Welcome back, Geometry, to another section in our quadrilaterals unit. This time we're going to be talking about trapezoids, specifically isosceles trapezoids. So for our definition, what it takes to be a trapezoid has one pair of opposite sides parallel. One pair of parallel sides. One pair of parallel sides. So this side here, these are the parallel ones. So when we talk about isosceles trapezoids, we're talking about trapezoids where these other sides are the same length, just like isosceles triangles have two sides the same length. So isosceles trapezoids also have, they do have the one-sided parallel sides, but they also have two sides that are congruent. The non-parallel sides are congruent. The non-parallel sides are congruent. Okay, non-parallel sides are congruent. That's what makes this isosceles. So when we just have that characteristic, if we just have the parallel sides, it's not very interesting. All we have is, there's not really any other properties that we can make use of other than the consecutive sides, or the consecutive angles rather, are supplementary, as they are with all parallel lines. So we're going to mostly talk about isosceles trapezoids to keep this interesting. So an isosceles trapezoid, one set of sides are parallel, as that property, as our defining trait, that part of our definition. The base angles in an isosceles trapezoid has the same property as the base angles in an isosceles triangle. So these two sides here, the two parallel sides, we're going to call those the bases, and when we call the base angles, those are congruent. Okay, so this is a base, this is a base, the parallel sides are the bases. So maybe this one could be base 1 and this one could be base 2, or vice versa. The two other sides we're going to call the legs. Or this is a leg and this is a leg. Just like on isosceles triangles. Okay? Difference here is we have this, imagine it's like an isosceles triangle where we chop off part of it. If we continue these sides, they would eventually meet as a triangle, right? So another thing about the isosceles trapezoid, the legs are, as we said, because it's isosceles, the legs are congruent. Legs are congruent. And in an isosceles trapezoid, the opposite angles aren't congruent like they are in parallelograms. The opposite angles, since the base angles are congruent, and the consecutive angles on the parallel lines are supplementary, the opposite angles will also be supplementary. Opposite angles are supplementary. So that's different from our other quadrilaterals so far. All of our other quadrilaterals have had opposite angles that are congruent. These opposite angles are not congruent, they are supplementary. Also in an isosceles trapezoid, we can say something about the diagonals as well. So I don't have the diagonals currently drawn in here, but if we draw the diagonals, as you might imagine, the diagonals will be congruent. If we think about those angles being congruent and those sides being congruent, well then this other side, they share that side. So we have basically a side angle side situation going on here to show that those diagonals, part of those triangles that are created with the leg and the base, those diagonals are congruent too. And then one last property that we don't have listed here but is going to be necessary for finding some of our missing pieces. This middle segment here, if these are the midpoints of the legs, if this is a midpoint and this is a midpoint, okay, if those are midpoints, then this segment in the middle here is called a mid-segment. Mid-segment. Sorry, my handwriting didn't quite make it there. Okay, mid-segment. I want you to add another property here, and we're going to say that in any trapezoid, a trapezoid, oops, goodness sake, in a trapezoid, the mid-segment is the average of the two bases. Lengths. Okay, the mid-segment is the length of the mid-segment is the average of the two base lengths. Okay, which makes sense if this has some measure, this has some measure. This measure being exactly halfway between them, we'll have the measure that's halfway between them. It's the average. So when we go and find our missing lengths here, if AB is 4 and EF is 8, that is the mid-segment. That's 4, that's 8. 8 is going to be halfway in between 4 and 12. Okay, so we can find that a couple different ways. We could find that just by counting, like 4, 8, 12, just counting by 4s. Or if we're thinking about the formula for that would be to find average, we add two numbers together and divide by 2. So if we call this base 1 and we call this base 2, base 1 plus base 2 divided by 2 gives us the mid-segment length. Well, we know that one's 4. We don't know what the other one is, but the mid-segment is 8. We can multiply both sides by 2 and then subtract 4 to find 12. Okay, so that mid-segment there is the average of the bases. So DC is 12. So if we know one and we know the mid-segment, we know one base, we know the mid-segment, it's easy to just count by whatever the difference is. The difference between 4 and 8 is 4, so the difference between 8 and the next one will also be 4. So 8 plus 4 is 12. To find our other measures, we're told AE is 6, and if E is the midpoint, then that would mean that ED is also 6. BF is also 6, and FC also 6. AD, that whole side length there, would be 12. And BF 6, FC 12, and BC 12. Oops, no, sorry, FC is 6. Okay, so the diagonal, or the legs are the same if this is an isosceles trapezoid. Finding the angles using our properties, EAB is 120, they tell us. So the base angles are congruent, so angle B is also 120. So ABF is also 120. BFE, this angle here, notice we have this top trapezoid. It's going to have all the same, it's also going to be an isosceles trapezoid, so it's going to have the same properties as the big trapezoid, just scaled down. So when I find this measure here, opposite angles or consecutive angles on the parallel lines are supplementary, so we can subtract 120 from 180 to find 60. And then the other angle also 60 degrees. And since these are corresponding angles, that one's also 60. So BFE, 60 degrees. AEF, also 60 degrees. CDE, also 60 degrees. EDC, is, oh, that's the same angle. CDE and EDC is just the same angle. EFC is, oh, this one is corresponding with that one. This one's 120, and this one's 120. So EFC is 120 degrees, and FED also 120 degrees. Okay. Let's see a couple other examples. So using this as an example, if JK is 7 and LM is 13, so JK is this one here, is 7, and LM is 13, what is CD, the mid-segment? So we said on the previous page, the mid-segment is the average. So average is, you add the numbers and divide by 2. So 13 plus 7 is 20, divided by 2 is 10. 10 is halfway between 13 and 7, so CD is 10. If the angle KDC is 52 degrees, what is the measure of angle JKD? JKD, this angle here. So these are supplementary, so we can say that 180 minus 52 is 130, nope, not 130, 128. So this is 128 degrees for that problem. Next up, we're told if JKD is 113 instead, so if it's not 128 and it's 113 instead, if it's 113 instead, what is the measure of angle M? Well, angle M is the angle that is opposite, and on the previous page we said that opposite angles are not congruent, but they are supplementary. So we're going to take 180 minus 113 to find 67. So 67 is how big angle M is if JKD is 113. If CD is 18, and JK is 12, what is LM? Well, we found out on the previous page that while we can find the average here, we can do what we did with midpoints if we need to find the other midpoint. With that, if we need to find the other side of this, if 18 is the average, you can find the difference instead and just count using that difference. So the difference between 18 and 12 is 6, so we can just count by 6s. 12, 18, 18 plus 6 then is 24. So LM is 24. So the average of 12 and 24 is 18. And that makes sense. We'll look at these last two together in class. If you want to try those on your own first, feel free. Otherwise, I will talk to you then. Bye for now.